Okay. Hello, everyone. Please start sitting down. We're going to start our first afternoon session that is going to be about single source studies. And the first talk of this session is going to be an invited talk by Kenzie Nimmo.
Okay, can everyone hear me? Yeah, okay. Can everyone hear me online?
Yes.
Yes.
Okay, perfect. Yeah, hi everyone. I'm Kenzie Nimmo. I'm a postdoc at MIT. I'd like to thank the organizers for inviting me to give this talk. And hopefully I'll give you an overview of the observational signatures of emission mechanisms for fast radio bursts. So I'll start with the big questions that I think about and lots of people in this room think about. Of course, there's the mystery about what kind of objects produce FRBs, and then also what the underlying physical processes are responsible for FRBs. And we heard great overview talks both today and yesterday on these topics. There's a wealth of information in the radio properties themselves of FRBs that hold information about both of these big questions. And we see a huge diversity in their radio properties, from their spectral properties, their temporal properties, their polarization properties. And the big question in my mind is this a reflection of progenitors? Is this a reflection of the emission physics? Or is it a reflection of the immediate environments? Or most likely some confusing, complicated picture of all of these mixed together. So to try and understand the emission physics part of this puzzle, let's think about what's broadly true in terms of FRB properties. So here I'm showing the transient phase space. We've seen this in a few talks already. Luminosity on the y-axis and duration on the x-axis. We can see that FRBs, which are in blue, they're coherent, so they have very high brightness temperatures. They are short duration, typically around millisecond timescales, and they're highly luminous, kind of 10 to the 32 ergs per second per hertz on this plot. They're also exclusively in radio, excluding the SGR 1935 burst, of course, and they've been seen from 110 megahertz all the way up to 8 gigahertz so far. And then finally, they're typically highly polarized. These are some bursts from R1, which we heard a nice overview of this morning. And yeah, they're kind of 100% linearly polarized across these bursts. So from these kind of broadly true properties arises the broad categories of FRB emission mechanisms. So I've put them into two classes here. You have processes that occur within the magnetosphere of a compact object, and then you have processes which happen further out. So the central object releases energy in the form of a shock, and that propagates really far out and produces the FRB at much larger distances. Of course, the picture is not quite this simple. We heard from Naveen yesterday that there's a lot of complicated models that fall under these categories. But for the purposes of this talk, I'm going to keep it really high level so that hopefully we can kind of go in one direction or the other. So in the question of are FRBs coming from a magnetospheric emission process or a non-magnetospheric emission process, I'm going to talk about these FRB properties that I've listed in the table. So we're going to look at their spectral behavior, their temporal variability, their polarization angle behavior, their circular polarization, and their scintillation. So starting with the spectral behavior, we've seen plots like this in a variety of talks already. FRBs can be broadband, but they can also be narrowband. And in Ziggy's paper, and then also in this the catalog 2 sample that we just heard about, there is a discrepancy between repeaters and non-repeaters in terms of their spectral properties. So repeaters tend to be more narrowband than non-repeaters. Is this because the repeaters and non-repeaters are different progenitors or different emission mechanisms? I don't know who has the badge that says that, but it's not me. There's also a suggestion that potentially this is a beaming effect, and that it's not due to differences in progenitors or emission mechanism. And then also for repeaters, we see the sad trombone effect or this downward drifting structure. This is R1. We saw these plots this morning from Jason, where you have these islands of emission that drift from high frequencies to low frequencies as a function of time. So are these properties, can we use these properties to distinguish between magnetospheric and non-magnetospheric models? Unfortunately, not. This behavior can be explained in both classes of models. This Metzger et al. 2022 paper that I cite here is a toy model of a narrowly peaked SED that is independent of the emission mechanism. So some physical realizations of this could be that in a magnetosphere, you could have radius to frequency mapping. So the emission site moves further out as a function of time to explain this behavior. And then for non-magnetospheric models, you could let the shock decelerate as a function of time, and that could also reproduce these results. But what about the timescales? So I said earlier, FRBs are milliseconds in duration. Well, we actually see a huge range of timescales in FRB emission, from 60 nanoseconds all the way up to second timescales. So there's really orders of magnitude difference here. Let's focus on the shortest timescales that we've seen so far, so 60 nanoseconds. If you just do a simple light travel time argument, you get to about 20 meters in emission radius from the 60 nanoseconds, so very, very small. And these small emission sizes are naturally explained in the magnetospheric models, so there's no problem here. However, that was excluding relativistic effects. If we take relativistic effects into account, there's this relationship here between the variability time, the emission radius, and the Lorentz factor gamma. And so you can see if you just bump up your Lorentz factor, then you can let your emission radius get larger. However, for the non-magnetospheric models, there is a similar relation between the width, the total width, and the emission radius. So not the variability time, but the total width. And so if you combine these two equations that have the same dependence on the Lorentz factor, then you basically say that the width has to be roughly equal to the variability time, which observationally is not true. We see orders of magnitude difference between the shortest time scales and the broader envelope in this repeating FB and also in other sources as well. So this definitely adds challenges to the non-magnetospheric models. However, there is a caveat that we did hear about yesterday in Naveen's talk, that if you introduce nonlinear propagation effects, then you can explain this variability in the shock models. So the idea here is you have the burst that's propagating through this plasma, and it gets split up into pancakes, or they're referred to in this Shaji et al. 2021 paper. And that introduces intensity modulations on a time scale that's equivalent to the radial width, like the size of these pancakes. And the prediction there is that you can kind of get into the microsecond regime timescale variability with this method. So yeah, all that to say that these short timescales and the variability are very strongly supported by the magnetospheric models. They point a little bit away from the non-magnetospheric models, but it's not really a slam dunk, can't be non-magnetospheric models. Okay, so what about polarization? Here I'm showing a plot of the polarization angles as a function of time for the first baseband catalog from CHIME. In the top panel, these are polarization angles that are flat as a function of time for a single component. And you can see that 50 out of the 88 FRBs in the sample exhibit this property. And then in the third panel, that's a flat polarization angle across multiple components. And you can see that there's 19 out of 88 that fit that description. And so a significant number of these 88 FRBs exhibit flat polarization angles across time. However, we do sometimes see jumps in the polarization angle, and even we've seen swings in the polarization angle. So changes in the polarization angle can be explained in magnetospheric models. We see this in pulsar emission. In the non-magnetospheric models, these jumps and even some smoothly varying polarization angles can be explained. However, in the case of this PA swing, FRB, the polarization angle swing is well fit by the rotating vector model that we see for pulsars. And that is really hard to explain without the interpretation of having a beam of light that's sweeping across your line of sight, like a pulsar, and therefore tying this emission to the rotation of the object, i.e. the emission must be coming from within the magnetosphere of this object. And so this swing points away from the non-magnetospheric models for this FRB. Furthermore, I did say that FRBs are typically highly polarized. Specifically, they're typically highly linearly polarized. You can see in this plot, this is a polarization study of the DSA sample of FRBs, where most of the FRBs are very high linear polarization and little to no circular polarization. Again, sometimes we see circular polarization, and in the literature, it's been reported up to 90% circular, so very high circular fractions. These circular polarization measurements are consistent with magnetospheric models. There's an interpretation that if you're looking at the emission straight down the beam of the emission of the burst, then you will see 100% linear. But as soon as you start to go a little bit off axis, then you'll start to see significant circular polarization. The same interpretation is true for non-magnetospheric models. However, the expectation is that the flux will significantly drop as you go more off axis. And at the moment, there's no obvious correlation between the flux of bursts and their circular polarization fractions. But furthermore, the prediction really is that the flux will drop so much that you won't even see it at cosmological distances. So that challenges this interpretation for the non-magnetospheric models. However, propagation effects can be introduced to explain significant circular. So there's things like Faraday conversion, where you would get significant circular fractions from propagating through that plasma. And so I have marked this one more as a question mark, since it's not naturally explained in the non-magnetospheric models. However, propagation effects can explain this behavior. Okay, the last property that I want to talk about is scintillation. So if people were at the November meeting, I presented on this result. So I'm not going to go into too much detail, but I'm happy to chat offline if people are interested. What I'm showing here is an autocorrelation function of an FRB spectrum. So we take the intensity as a function of frequency, we autocorrelate it, and in this autocorrelation function, we see two clear Lorentzians. And Lorentzians are the expected functional form for scintillation. And in this work, we interpret these scintillation scales, one being from a plasma screen within the Milky Way, and the other from a plasma screen in the FRB's host galaxy. As we heard from Rob yesterday in a great overview talk, when you have two scintillation scales or scintillation and scattering measurements, you can use that the coherence of scintillation to place a constraint on where those screens are, but also to use it to put a constraint on the size of the emission region. The analogy that Rob made and that I'll also bring up is stars and planets. So stars, they twinkle because of scintillation from Earth's atmosphere. This is because they're far enough away that they're a point source with respect to the diffractive scale of Earth's atmosphere, whereas planets are closer, and so they appear larger, they're spatially resolved, and you lose that coherence and you don't see scintillation anymore. The same is true for FRB emission. If we have this plasma screen in the host galaxy, then we know that the FRB site has to be a point source-like with respect to that screen. And so you can use that logic to place a constraint on the size of the emission region. And in this case, we were able to place an upper limit of 3 × 10⁴ kilometers on this emission radius. Again, like I mentioned, for the temporal properties, really small emission region sizes are naturally explained in the magnetospheric models, where you expect really small emission regions. And for the non-magnetospheric models, you kind of expect 10 to the 5 kilometers and higher. So out with the upper limit that we place. And so this measurement of the emission size, this constraint on the emission size, disfavors the non-magnetospheric models for this FRB. So as you can see from this table, there is growing support for the magnetospheric models in the studies that I've presented. And there's some challenges to the non-magnetospheric models with caveats that just are not so naturally explained, that can't naturally explain the emission properties that I've mentioned here. However, I don't think that that's kind of the end of the story. I actually think that there is evidence for multiple emission mechanisms. I'm showing two bursts here from two different repeating FRBs. And they're showing very similar morphological structure. So you have these kind of sharp components on top of a broad drifty envelope. You have some wider components that look like maybe they're changing in their dispersion measure or maybe changing their drifting properties. And in this Hewitt et al. 2023 paper, the analogy is drawn to solar flares. And I think Jason also mentioned it earlier today, where in solar flare emission, you can get these kind of sharp structures that are thought to come from magnetic reconnection happening near the solar surface. And the broad drifty components are thought to come from shocks that propagate out into the corona. So quite analogous to our magnetospheric and non-magnetospheric models. Of course, solar flares are at totally different energies, frequencies, timescales, but at least morphologically, the analogy is there. And then moreover, there's this growing evidence that repeating FRBs exhibit this break in the energy distribution. I'll refer to Omar's presentation following me, who I think will go into a little bit more detail on this. But when I see these, I think is the emission physics for these low energy bursts the same as those in the high energy tail, or do we have different physical processes driving these different distributions? And I think to tie back to the scintillation result, which I think is a really powerful tool in understanding the emission physics, it would be really great if we could explore if the scintillation properties in these low energy bursts compared to the high energy bursts differ, pointing towards different emission radiuses or emission processes. Okay, so to summarize, we have this diversity in radio properties that potentially indicates a mess of progenitors and emission processes and immediate environments that are all confused together. But we are working to disentangle this actively. So I only talked about emission processes, but of course we've heard many great talks on looking at the host galaxies and local environments of FRBs, which tells us about their progenitors. And I'll highlight again, I think it's been in every talk at this point, but I'll highlight again the recent CHIME FRB outrigger localization of a non-repeating FRB and refer to Mawson's talk later on in the week. For the immediate environments, Rob gave a great overview of the different propagation effects that we can see in FRBs, and that gives us a wealth of information of about the plasmas that the FRB propagates through on its way to Earth. And I wanted to highlight this cool result that I thought was interesting of a repeating FRB study by FAST, where they see that the rotation measures pretty flat with time for a very long time, and then out of nowhere it flares and jumps up by over an order of magnitude in the RM. And the interpretation there is that that there's this magnetized flare of plasma potentially from a companion, a binary companion, driving this RM behavior. And then, of course, the emission processes. We have a lot of interesting observables in the FRB population, and they are pointing towards a magnetospheric model in these cases. The big caveat is the session title, single sources. Basically, everything I talk about are kind of individual sources or small sample studies. And so it's very unclear whether or not this table is really reflective of the entire population or whether we've just been able to do these really detailed studies on individual weird FRBs that don't really reflect the broader population. And so, yeah, I'm really interested in scaling up these efforts. CHIME has thousands of FRBs, so we should be able to, scale up all of these observables and really explore the emission physics broadly for the FRB population. Thank you, and I'll take any questions.
Thanks, Kenzie, for keeping to the time and for an amazing talk. Do we have any questions? Okay, there's one online. So do we have the catch box? Okay, yeah.
Yeah, so we have a question online in the chat that says, can the non-existence of sad trombone drifts at high frequencies above 4 gigahertz provide evidence that the frequency time structure is strongly coupled to propagation effects and not as much to the emission geometry?
That's a good question. So I think broadly, we don't really understand the like the drift rate of these, the sad trombone effect. So it's possible that there's some frequency dependence on the drift rate, that it could be slower at high frequencies, and therefore you wouldn't see it observationally. I guess the one argument against it being a propagation effect that I've heard is that for plasma lensing, you would expect it to go equally downward drifting and upward drifting. And we typically see it downward drifting, and very rarely do we see upward drifting structure. And so I think that data point at least pushes it away from a propagation effect. But the frequency dependence of this and the driftiness of them is, I would say, not well studied.
Cool. Other questions? Over there, we could send the catch book.
Hi, Martin Topinka from Cagliari. I wanted to ask about the Lorentz factor. You mentioned what are the typical values? They're like assumed, or is there any way how to directly observe for a particular FRB the Lorentz factor somehow using the particular model?
Yeah, I think the Lorentz factor is very unconstrained. I've seen numbers kind of in the hundreds, thousands, maybe higher, reported in the literature, not measurements, but from models. In terms of measuring or constraining the Lorentz factor, I think if we could have if we could take like temporal variability as a constraint on the emission size, as well as the scintillation simultaneously, you could probably combine those measurements or those constraints to place a constraint on the Lorentz factor. Yeah, if we could see it in the same burst, potentially.
Okay, I think there was another question in the room. Yeah.
Hi, this is Laura Spitler. So I have a question. You mentioned, you talked about the polarization position angle, either flat or swings within a single burst. I'm curious if you take that and then you have multiple bursts from a repeater on, say, like a time scale of an hour. Can you comment on how constraining, say, them all having the same PA over the hour versus like PAs jumping from burst to burst is in constraining one of these two origins?
I think it's not constraining because I know that the both models can have different polarization angles for independent bursts. The variation, the interpretation of the variation, the PA swing is rotation. So unless the repeat bursts are kind of within the rotation of the object and you're seeing essentially like discrete patches of the RVM, then I think it wouldn't distinguish between magnetospheric and non-magnetospheric models. However, I know like polarization behavior in repeaters, there's like proposals that you could use it to constrain like a precessing neutron star. Like in the case of R3, for example, you could use the PA behavior to discuss between like a binary model or a precessing neutron star. So there's maybe like bigger picture questions, like progenitor questions you could answer. I'm not sure on the emission physics.
Okay, we have time for one last question. Yeah.
Oh, okay. So It's my turn. Okay. Hi. So, I just can you hear me?
Yes.
Oh, okay. So I just want to add two very quick points. So for the spectrum behavior, actually the shock model also cannot explain, I mean, the narrow spectrum. So if you use the relative bandwidth delta nu over nu, you will see many repeating FRBs have the typical value from 0.1 to 0.3. But if you have a very large shock structure due to the high latitude effect, this will cause the delta nu over nu much greater than the observed values. And another thing is, so you mentioned the nonlinear propagation effect, the filamentation instability. Roughly at 3 years ago, there's a paper by Wenbin, Pat Binyamini, and Pawan Kumar. They calculate in order to satisfy the observed variability time scale, actually the growth rate of the filamentation instability is very low. So maybe it still cannot explain why we see so small variability time scale. Okay.
Yeah. Yeah, I appreciate your comments. I think on the topic of the narrow bandedness, like I referred to the Metzger et al. 2022 toy model, which has a few physical realizations. So it's not broadly applicable to all non-magnetospheric models, but there are instances in which you can explain the narrow bandedness. And then for the temporal variability, I agree with you, and I've read the Benyamini and Kumar paper. I think the timescales still are maybe a little bit off, but it does in terms of the these nonlinear effects kind of are in the kind of tens of microseconds regime, and we've seen down to 60 nanoseconds. So there's still quite a jump in those timescales that is unexplained from these nonlinear effects, but it does make me a little bit concerned about the I guess slam dunk-ness of temporal variability for magnetospheric versus non-magnetospheric. But I mean, Naveen's talk yesterday highlighted nonlinear effects and kind of highlighted that more studies on these kind of propagation effects are really needed to understand this better.
Okay, thanks.
Thank you.
We can chat.
Okay, if you have any more questions, could you please ask them on Slack or during the coffee break? And let's thank our speaker again. Okay, our next speaker is Omar Ould-Boukattine, who will talk about apparent DM and RM changes from a repeating FRB source.
Thank you. Can everybody hear me clear? Great. Apparent dispersion measure and rotation measure changes from a repeating fast radio burst source. My name is Omar Ould-Boukattine. I'm a PhD candidate in the AstroFlash team, which is hosted here at McGill, at Astron, and the University of Amsterdam. I'm happy here to speak to you at FRB 2025. And we all have a common goal. We all try and get a little bit closer into answering the question, where are FRBs coming from? Why are they happening, etc. And I think in order to study these things, we have to really zoom into the local environment. And you can do this, study the local environment using propagation effects, as we heard yesterday. And you can do this for one-off sources, for which we'll hear more about later this week. But if you want to study time variability in propagation effects, then you would need naturally a repeating source. But studying, so two of the most studied propagation effects, or the most profound propagation effects, are dispersion and rotation measure. But finding and claiming variability on these two properties is non-trivial and requires great data, but also a special source in that sense. And I do my observations using an array of telescopes located in Europe. They're rather small, 25 to 32 meters. It's the Westerbork telescope in the Netherlands, the Onsala telescope in Sweden, the Stocker telescope in Germany, the Dwingelo telescopes in the Netherlands, and the 32-meter Torun telescope located in Poland. We do not work interferometrically, but individually at complementary wavelengths, and we observe as much as we can. So to give you an indication, last year with Westerbork, I conducted more than 6,500 hours of follow-up studies for repeating sources. Of that, like 1/1,000,000% is like actual data, but you know, quite a lot of hours. Collectively, we call ourselves Hyperflash, and our aim is to do high cadence monitoring to observe the brightest and therefore also the rarest FRBs. We have another high cadence monitoring program within the Astroflash team in Europe, which is the ECLA initiative, making use of the Nancy radio telescopes, which is this giant wall, but it's equivalently sensitive to a 100-meter telescope. Its PI is Dante Hewitt, and it's supported by Sylvain Ranguin and Jeff Huang. So now that we know our telescopes, we need a source. So I was very happy that in the middle of 2024, the Meertrap team released an ATEL by Tian et al. On FRB 2024-06-19D. And after the release of this ATEL, it took us 13 hours to be on source, and we conducted a high cadence monitoring campaign. A week later, we released our own ATEL on the bright detection of a single FRB. This is using a 25-meter telescope in Europe, and when coherently correct for the dispersion measure, we exceed the signal to noise of over 1200. So it's basically a delta function. It is close to 1,000 Jansky milliseconds, and I think it's one of the highlights for the Westerbork sample. In total, we observed for more than 500 hours in 4 months and achieved more than 200 detections. I want to highlight here that this wouldn't have been possible without the release of the ATEL. Astronomers' telegrams, for me as follow-up researcher, are extremely important. So whenever I make a detection or find the reactivation of an FRB, I try to communicate that via the ATEL. So VO events and the astronomer telegram are vital to do the follow-up monitoring. Another detection I would like to highlight is the detection we did with the Dwingelo telescope, which in 1956 was the largest radio telescope in the world. But has now been repurposed such that we can also try and detect fast radio bursts with it. The reason why Max is on this slide is you have to be physically present in the dish in order to do observations. Unluckily for Max, the source was only visible between 3 and 5 a.m. during the times of the ATEL, but he spent nights there, and not without any success, he detected this very bright FRB. And as you can see on the top panel, I quote intensity, because in order to quote signal to noise, you would need noise. There is no noise because everything is RFI, because the telescope is located next to the headquarters of Astron, and there's all types of RFI environments. So it's just signal, but there is an FRB there. So now let's look at the collective properties of all the detections which we have. The cumulative burst energy distribution. On the y-axis, we have rate, the amount of bursts you can expect per hour above a certain energy. And on the x-axis, we have fluence in Jansky milliseconds. So now let's just add all the bursts, and we find that the energy distribution breaks towards higher energies. This is not the first time you've heard this. If you paid attention in last talk by Kenzie, you saw other examples. But I also mentioned this at other conferences in the last years, and I'm very happy that you all remembered it. But I'll put them up. For FRB 2020-1124A and 2022-0912A, we find a similar behavior where the energy distribution breaks towards higher energies. I want to emphasize that this is only possible due to high cadence monitoring, so making use of hyperflash in this case. You could see basically the left side of the energy distribution. If you have a sensitive telescope, you detect all the weaker bursts. And on the right side, you do not need a more sensitive telescope to detect these bursts. You just need time. I have lots of time. So therefore, we can try and detect these bursts. And I see you wondering, there's this old circle there. That shows that it indicates that perhaps the Nancy radio telescope could also detect that break, but due to the observing hours, we were not able to probe the high energy tail only using the Nancy sample. But it is a very bright FRB, close to 1,000 Jansky milliseconds, with a telescope which is roughly 100 meters. So how would the dynamic spectrum look like? That's this. It's the same burst that was detected by Westerbork. At the bottom, I show the waterfall. We use waterfall plot. We show a custom color scale because otherwise you wouldn't see anything because it's so incredibly bright. In the middle, I show the time series using the polarimetric properties. We plot this in log scale because the signal to noise exceeds over 6,000. So we do need log scale here. And at the top, I show the P3A, which is relatively flat and is comparable with the results found in the discovery paper by Tian et al. Notice that the DM, it has been corrected for dispersion, and all the smaller components all align with this main dispersion. So we're able to measure the polarimetric properties for the burst sample for the Nancy radio telescope. So what we did for the 5 epochs for which we had detections, we took the 2 brightest detections of each day and measured its rotation measure over time, which I show on the following plot. So here on the right, I show rotation measure plotted over time, and we find that it isn't constant. It's changing over time, roughly 100 radians per square meter in a month. So that's the first time variable propagation effect. Now let's look at the sample detected by Westerbork. Here I plot them all at the same time and frequency resolution, so it's easy for you to spot the differences. The first one that I see, and I also want to highlight, is the fact that the temporal range is quite broad. For one burst, I show 5 milliseconds. On the other, I show 50. So there's quite a range, again, for this sample. But as you can also see, there are also unresolved components to these bursts. Luckily, at Westerbork, we record with baseband mode, which means it's a pitfall. You can do all the time resolutions which you like, but we can go to higher time resolutions. So now let's take the brightest burst here, which exceeds the signal to noise, comes close to that 1300, and look at that at 1 microsecond, when it's still signal to noise 450. I plotted at minus and plus 0.1 parsecs per cubic centimeter to indicate that the middle is the actual correct DM. And you can do this over a trial of DMs, right? And then take the peak signal to noise, create a curve, and assuming that it is completely straight in a single component, you can very accurately determine the dispersion measure. So we did that. And we find that this is the most accurate dispersion measure for this burst. Now let's take it for a burst detected a week later. Every step we take here in dispersion versus signal to noise is coherently done. So this is a week later, 1 microsecond. We take a burst detected another week later. As you notice, in the signal to noise versus DM column, the x-axis is shared, indicating that the dispersion measure is evolving over time. So let's take the 5 measurements for which we have can accurately determine the dispersion measure, and we find that it is increasing over time. A total of 0.4 units in roughly 2 months. We did it. Time variable propagation effects. What can you do with it? This is great. Now we have post stamps. We have stamps. We collected them. It's great. What do we do with it? As you probably all paid attention yesterday, we can now try and calculate the parallel magnetic field strength. And we did that, and we found it to be 0.3 with an error of 0.2 milligauss. The large error comes from the errors which we have on the rotation measure. And the first time that we calculated this, I was like, great. What does 0.3 milligauss mean? So you go back where you always start, the fundamentals, the handbook for pulsar astronomy. You turn to page 87, the interstellar medium, and you find that it's roughly a microgauss. So we are already 300 times higher than a microgauss. So let's compare it to a sample of repeating sources. The first one being the first repeater, 2012 11028, where they calculate the parallel magnetic field strength to be between 0.6 and 2.4 milligauss. So that's a factor of 2 to 5. Then there is the FRB 2019-0520B, also known as the R1 twin, by Reshma and Thomas. And there they calculate the parallel magnetic field strength to be between 3 and 6 milligauss, which is an order of magnitude away from what we currently have. The conclusions for both these sources was that it is in a dense magnetic environment. And where we conclude what our sources lie within these 2 numbers is that it's not in a as dense magnetic environment, but in a relatively dense magnetic environment. And that's the main conclusions. If you have any questions, you would like to discuss this further, you would like to collaborate with Hyperflash, let's chat. I brought stroopwafels. The other members of our team also have access to these stroopwafels. So if you want to ask them questions, that's also possible. We also have katja biggetjes, which are gluten-free variant of the stroopwafels. And I'll leave you with my summary slides. And if you have any questions, I'll be happy to answer them.
Thanks, Omar, for a really nice talk. Do we have any questions from the public? See one there.
Okay.
Hey, thanks for the really interesting talk. I'm Pavan from Swinburne University. This is probably a naive question, but do you see a similar trend when you structure maximize the bursts and instead of doing the SNR maximization for the DM?
For the which?
For the DM evolution.
For which DM? Oh, I'm sorry, I don't understand your question.
Oh, I mean, I think you were mentioning about the SNR maximization for estimation of the DM.
Yeah.
Do you see a similar trend when you structure maximize it rather than just SNR maximizing it?
We are SNR maximizing every burst. That's how we determine we don't do structure optimizing. We just do signal to noise optimizing in that sense.
Right. So do you see a similar trend in evolution of
Oh,
DM?
right. No, we didn't do that because we just do signal to noise optimizing and we don't see any need to do structure optimizing in that sense. Yeah, because we did the old pay trick and this is pretty strict. Like I can't get this DM better for these bursts. Yeah.
Thanks.
Hope that helps.
Kavya, behind you.
Oh.
Hi, nice talk. I was just interested in the last date of the last DM estimate you had. So the DM was consistently increasing. So the last day was.
Okay. It's somewhere. Is that what you mean?
Okay. So it was 8th of August. Sorry, 18th of August. Last year. Okay, yeah. Because I also had observations after that.
Mm-hmm.
And the median DM estimates from that showed like the DM was like reverting. So it was like fluctuating. So the median estimate was not secularly increasing, but it was showing this fluctuation.
Yeah, that is varying. Yeah.
Yeah.
What we try and do also in the paper is not interpret this as linear, even though we see 4 points increasing. We try not say it's linear. And when we do the calculation for the parallel magnetic field strength, notice that the overlap where the DM and the RM are actually where we both have the samples at the same time. That's where over that change, that's where we calculate parallel magnetic field strength.
Okay.
So we don't do that for the calculations after 18th of August because we don't have any RM measurements there. Yeah.
Okay, thank you.
There's time for one short question, so maybe the person online can ask or.
Thanks. This is just a clarification question. Is the inferred B this also varying with time? They say they missed this.
Is that also varying with time? Well, if there's another activity period of this source and we find the same variations in DM and RM, then we can try and see if it's consistent or not. But it was just made on the single observation that we have DM and RM changing over time in that sense. Yeah. Yeah. So we can't quote multiple numbers because there's not multiple epochs yet. We just have to be hopeful.
Okay, so if there's more questions, please talk to Omar during the coffee break. He has stroopwafels, or you can ask them on Slack as well. So another.
Thank you.
Thank you.
Right.
Yes. Yeah. Okay, so our next speaker is Alexandra Moroianu. Please take it. Thank you.
Hi everyone, my name is Alex. I'm a PhD student who's part of the AstroFlash team at the University of Amsterdam, co-advised by Jason Hessel, Ziggy Punis, and Benito Marcote. And today I'm going to be talking about our milliarcsecond EVN localization of the high DM repeating FRB 2019-0417A and its candidate PRS. So as we know, one of the ways we can sort of learn more about what FRB origins may be is through FRB localization. And today, FRB localization is better than ever with new and existing instruments such as the Chime Outriggers, ASCAP, Meerkat, DSA 110, just to name a few. Through these, we're able to achieve arcsecond, or in the case of the Outriggers, 50 to 100 milliarcsecond precision for both repeating and non-repeating FRBs. So the number of localized FRBs we have is steadily growing, and it's a very exciting time. That being said, milliarcsecond precision localization is still important. And by milliarcsecond in this case, I mean a few milliarcseconds, to the point where we're able to zoom in on the local environments of FRBs down to parsec scales. And the only way we can achieve this is through very long baseline interferometry, VLBI. And I'm part of the PRECISE project, which uses the EVN to follow up repeating FRBs, usually FRBs first detected by Chime, to zoom in on their local environments. And this has revealed a diversity of FRB environments, but one of the most exciting results that has come out of VLBI observations of FRBs is entering the era of persistent radio sources. So persistent radio sources, or PRSs, as most of us know, are non-thermal luminous sources of persistent radio emission that are compact on VLBI scales and have been found to be coincident with a rare few FRBs, around 3% of localized FRBs. And these FRBs tend to share quite similar properties. I'm going to be focusing on these two, 121102A, the first repeater, or R1, and FRB 2019-0520B, also dubbed the R1 twin due to their similarities. So both of these FRBs are repeaters. They have large and extremely variable rotation measures and generally pretty high DM host contributions, specifically in the case of 2019-0520B. The PRSs, so as I said, they've been found to be spatially coincident with PRSs, and these PRSs have been constrained to sub a few parsecs. They have negative spectral indices in the case of these two sources around negative 0.4, very luminous with luminosities around 10 to the 29 ergs per second per hertz, and they are both in low metallicity star-forming dwarf galaxies. Interestingly, 2024-0114A has also recently been localized to a low metallicity SMC-like satellite galaxy. So it also does share these properties, but this FRB doesn't have as high and variable of a rotation measure, for example. Introducing FRB 2019-0417A. This is a repeating FRB discovered by Chime in 2019. It's specifically interesting because, as you can see on the graph on the left, the orange histogram is the extragalactic DM contribution or distribution of 40 repeating Chime FRBs. And this FRB very much sits at the tail with a high DM of around 1,380 parsecs per centimeters cubed. It's also got a high rotation measure of around 4,600 radians per meter squared, though this is slightly lower than R1 and its twin. And it has a candidate PRS identified by Ebic et al. So you can see in the image on the right, the red ellipse is the Chime localization, and the source S1 is the candidate persistent radio source associated with a dwarf galaxy host at a redshift of around 0.13. So obviously, the localization region of this FRB by Chime is 1 arc minute in diameter, so we can't definitively say anything about this association. What we did with PRECISE was we observed this source with the EVN during 7 observation epochs from February to August in 2022. During these epochs, we detected 8 bursts, 5 of which had a high enough SNR and didn't show significant ionospheric variations or errors that we used for a EVN localization. So for reference, when we have 1 burst, as you can see in the image on the left from our 2024, we tend to have multiple equally bright peaks when it comes to the localization. This GIF zooms into a 500 by 500 milliarcsecond region, essentially the same size as the ellipse in the image on the left. And the more bursts we add in, the more of the UV space we sample. We eventually ended up with a localization of this FRB at this nominal position plus or minus 5 milliarcseconds. So we were able to localize this FRB to around the size of the EVN beam. The next question is, did we see a PRS in the continuum data? So we did indeed see a PRS that is still compact on EVN scales. It is consistent with the position quoted in Ibika et 2024, has an integrated flux density of around 190 microjanskis, a radioluminosity of around 7 times 10 to the 28 ergs per second per hertz. We have a conservative size constraint of a maximum of 35 parsecs. For reference, the Crab Nebula is around 3.4 parsecs in diameter, so we want to observe this in higher radio frequencies so we can constrain the size further. But overall, properties are consistent with those quoted in Ibika et 2024. The next question is, are FRB 2019-0417A and the PRS still spatially coincident? And the answer is very much so, within 10 milliarcseconds, corresponding to a maximum offset of 25 parsecs between the two sources. But you can see the FRB dirty map is the background image, and the EVN position of the PRS lies right on top of the FRB localization. So we have officially confirmed another FRB PRS system. What are the properties of this new system? So Dante Hewitt from our team did an RM analysis and found that the RM varied between around 3,900 and 5,000 radians per meter squared. So there is indeed a variable rotation measure, and a new paper on the archive led by Feng et al. Confirms that they also saw this variability. The most probable DM host we derived had a lower limit of around 550 parsecs per centimeters cubed, so an extremely high DM host contribution, and a 3-year DM variability with a maximum of 1 parsec per centimeters cubed. Essentially, we did not observe any DM variability in this source. Again, the PRS has been shown to be compact, had an in-band spectral index of -1.2, very luminous, and in a low metallicity star-forming dwarf galaxy. We also note that its properties, I took this image from the Bruni et al. 2024 paper, but it does lie on the luminosity RM relation that has been quoted in a few papers. So it's consistent with other FRB PRS systems in this regard. What's specifically interesting is now with another confirmed FRB PRS system, we're starting to see that these systems predominantly occur in low metallicity dwarf galaxies. And as we heard from earlier talks, these past 2 days, that's different from the majority of FRBs. So plotted here in green is the host properties of repeating and non-repeating FRBs, in this case, R-band magnitude versus redshift. This was done by Maria Drout and Daisy Ibik. And you can see in color here at the bottom is where FRB PRS systems lie. So they're in lower mass, fainter dwarf galaxies. But what's even more interesting is when you plot the metallicity versus the mass of FRB host galaxies, in green is the majority of FRB hosts, but then FRB PRS systems are located here, and 2024-0114A is also located in the purple square, making their hosts more consistent with those of long gamma ray bursts and superluminous supernovae. So what does this mean? Do these systems imply one or multiple classes of repeaters? This is still an open question, but there's a few possible explanations that could explain why FRB PRS systems have these properties and occur in these host galaxies. One is a continuum scenario. And what I mean by this is PRS FRBs could potentially be the youngest repeaters, or alternatively, and what is probably more likely, is they could be the repeaters that are born in extreme low metallicity environments. So low metallicity dwarf galaxies have less wind. In this case, magnetars could possibly be born with higher spins and dump a lot of dense matter, which would explain the high DMs and high rotation measures that we see. A lot of models, for example, one for magnetar wind nebulas proposed by Rahman et al. In 2025, say that in this case, we would expect the PRS to fade around within 10 to 100 years. So these are very young systems. Alternatively, there's a possibility that they're a unique engine, for example, a massive accreting system, or a separate class of repeaters altogether. One thing that could potentially justify this is it's been shown that black hole mass and galaxy size tend to scale together. So it could be that, you know, these PRSs are explained by a massive accreting system. In this case, we'd expect a long-lived PRS with minimal dispersion measure and luminosity evolution. And potentially we'd expect the rotation measure variability to remain. But both these cases could explain why FRB PRS systems are rare, either because they're quite young or just because they're rare emitters of FRBs. So in overall, FRB 2019-0417A adds to the growing subclass of PRS-associated repeaters. We've officially confirmed another FRB PRS system, and we found that it shares quite similar properties with those of R1 and its twin, though it can be argued that maybe it's a less extreme version and a bridging source between that and FRB PRS systems like 2024-0114A. But we're starting to see a pattern emerge here. For example, the fact that they're all in these low metallicity dwarf galaxies kind of differentiates them from other FRBs, which is interesting. So a lot of additional questions. And that's it. Yeah, I'm happy to take any questions.
Thanks, Alex. Really exciting results. Do we have any questions? Okay, so we have Kavya. So
Thank you very much, Alex. So that was a great result. So I was like, sorry if I have missed it already. I was just checking whether you had removed any bursts detected during the observation while imaging and looking for the PRS.
So we didn't remove any bursts, but we do have about 30 hours or so on the PRS in this case. So it wouldn't be expected because none of these bursts were really bright as well. It was all just kind of like SNR of around 9. So we wouldn't expect them to be kind of making a false PRS, if that makes sense in this case. But we will do that to double check.
Thank you.
okay, we have another question over there. So maybe someone in between.
Hey, Alex, this is Calvin from Berkeley. Great talk. I was wondering if you expect along the line of sight for groups or clusters and what the scattering timescale of this burst is. The DM excess and the 35 parsec transverse size seems to imply very high electron density in the local environment.
So there's a few things that we're still finalizing. A lot of it is in prep. So I can't give you an exact answer on the scattering timescale, but regarding checking for clusters in the line of sight, we haven't seen any obvious ones. I still need to do this, but we are currently doing a bit of a simulation. When I said that there's a lower limit of around 550 of DM host, this was assuming a kind of optimistic or conservative DM halos contribution. But right now we know that to explain the sort of excess DM, we would expect an intervening halos contribution of around 800. So we're trying to figure out like what scenario of intervening halos we would need to explain that away. And one of the ways we'll do that is by looking at archival data to see if we see evidence of a cluster. But right now, just from the preliminary results, we haven't.
Sounds good. Thank you.
Do we have another short question? And if not, you can ask Alex during the coffee break again. Let's thank her again.
Was this yours? Yeah. It takes a second.
Hello, I think.
Okay. Our next speaker is Kavya Shaji, who will talk about long-term observations of FRB 2024-0619D and R1.
So, good afternoon, everyone. I'm Kavya Shaji, and I'm a second-year PhD student at University of Sydney. So, I'm giving this talk on behalf of the entire MeetUp collaboration, and I'll be discussing some of our interesting results from long-term monitoring of 2 repeating FRBs. The first MeetUp repeater, FRB 2024-0619D, and the well-studied first repeater, FRB 121102A, also called as R1. So, thanks to Kaustubh and Ben, who gave like a detailed overview of the MeetUp backend in transient searches. So MeetUp discovered FRB 2024-0619D on last year, June, and it was initially discovered with a signal-to-noise maximizing DM of 486. And the source was localized using the transient buffer voltage data, achieving a positional uncertainty less than 1 arcseconds. And we find no significant optical counterpart in any of the archival images. And subsequent detections from GMRT, Westerbork, and also Meerkat confirms the source's hyperactivity as discussed by in Omar's talk. So hyperactive repeaters are characterized by their exceptionally high burst rate, often emitting tens to hundreds of bursts per hour, which is like significantly exceeding the activity levels of typical repeating FRBs. And follow-up observations of hyperactive repeating FRBs have been extremely successful in revealing many of the properties such as like spectral as well as temporal evolution of the burst activity and burst properties, which are very valuable in constraining the different emission mechanisms and progenitor models. So we have been following up this source with Parkes or Moroianu telescope, Meerkat, Lovell, and Atka. We were having high cadence and long-term observation. So in the first session of my talk, I'll be discussing the results from that high cadence monitoring. So our observation revealed an extremely high burst rate with a total of 1,500 bursts detected with Meerkat, Lovell, and Moroianu, spanning a frequency range from 0.5 to 4 gigahertz. Moroianu alone detected nearly 1,100 bursts, benefiting its wide bandwidth and sensitivity. So in the first plot, I show the burst rate variation with the time and frequency. So the filled markers indicates the detections and unfilled markers indicate non-detections with a 95% confidence Poisson error bars on them. So the source was active until 4th of September, after which we did not detect any further bursts, but the long-term monitoring is still going on. So what stands out is the source is exhibiting like clustering in like a temporal clustering in its activity. So we found an estimated 350 bursts per hour in early August. Then we found a sharp decline in the burst activity. So, and the figure on the right side shows this scatter plot of the bandwidth, measured bandwidth and width distribution of the burst. So nearly 40% of the bursts detected are very narrow banded, having bandwidth less than 100 megahertz. Also, we find strong frequency dependence in the emission. Again, 40% of the total detected bursts are detected between 1.4 to 1.7 gigahertz. Such a frequency-dependent emission is also seen in other repeaters such as R1 and R2. Again, taken together, confirming that like such a frequency-dependent emission could be something intrinsic to repeating FRBs, unlikely to be solely due to propagation effects. So here I just show a subset of the bursts detected from Moroianu. And detailed analysis of such as spectrotemporal polarimetric properties of the burst from the source detected with Meerkat has already been analyzed and published by June Tian this year. So here I just discussed the results from Moroianu. So out of the total detected 1,100 bursts, 80 bursts detected resulted in a measurable RM. And we find that most of the bursts are linearly polarized, nearly 97% of them. And 3 bursts exhibit significant circular polarization. And this occasional circular polarization and high linear polarization again support magnetospheric origin processes. Also, we find modest variation in the polarization angle in 17 of the total 80 bursts. Also, 24 of the bursts are like microseconds, like hundreds of microseconds in duration, but they are resolution limited, indicating they can be even narrow in time or can consist of unresolved substructures, again supporting compact and coherent emission regions. So here I just show the RM evolution of the source. So as discussed by Omar in his talk, we like I haven't like tried to check a correlated evolution in DM and RM within a single day, but that would be something great to do. So here I just show the median estimates of the RM as a fitted trend line. So we find that the magnitude of the RM is increasing at a rate of 1.85 rad per meter square per day. And so I think I have got the signs wrong here. And we find that the DM of the source is like not evolving, because nearly in the start of the September, we found that the DM value again went back to around 464. So we find that there is no correlated evolution in the DM values, but up to a limit of 1 to 2 parsec per cubic centimeter, which is also again something to be investigated. So several repeating FRBs such as like 1903-03A and also 1809-16B. Here also I think I got a sign wrong. The RM is increasing in the case of, here the RM is increasing in the case of 1903-03A, and they don't have any correlated evolution in the DM. It might actually indicates that the DM and RM are arising from different regions around the progenitor, or the Faraday rotation evolution is solely contributed by evolution in the magnetic fields. Also, we looked for a periodicity in the burst arrival times. So we just simply ran a Lomskagel periodogram, and we find no periodicity in the burst arrival times, but robust analysis on the periodicity is also yet to be undertaken. And the wait time distribution of the burst is also analyzed. So this plot shows the density plots of the wait time distribution with the observed data compared with a Weibull fit. So we find that the Weibull distribution with a shape parameter value less than 1 is actually giving a reasonable fit to the observed wait time distribution, indicating clustering in the burst arrival times. So repeaters like R1 and R2 is also shown to exhibit such a clustering in activity, which is also something to be done with the emission mechanism. Also, we searched for the presence of a PRS near the source with spanning a frequency range from 0.5 to 12 gigahertz with Meerkat and Atka. So here I just show the continuum images from Meerkat at L, U, and S bands. So we found no PRS, but only upper limits. But here also I want to make a point that we did image this source after removing the burst detected during the observations. Otherwise, we were seeing a continuous and compact emission near the source. Once we remove the burst, we find there is no continuous emission, and it was solely due to integrated burst. Also, we searched for the PRS with Atka, but because of the sparse UV coverage, we are keeping upper limit on the flux density of the order of 1 millijansky. So now coming to the second source, which is the well-studied repeater, thanks to the morning session for the detailed history of this source. So METRAP collaboration has been already monitoring this source from 2019 and continuing through 2025. The observations are conducted by deploying the simultaneous beamforming and imaging backends of Meerkat, which allows us to look for any potential correlation between the properties of the PRS itself and also the burst. So the data from this initial monitoring was analyzed and published by, and so for the details, you can look at Manisha's and Lawrence's paper. So here I will discuss some of the other results from this monitoring campaign. So here I just show the DM estimates of this source from Meerkat compared with those values reported in literature. We find that the DM of this source is declining at a rate of 0.01 parsec per cubic centimeter each day. And this rate is also consistent with the results from FAST, indicating that there is a potential evolution in the ionic environment around the progenitor of the R1, possibly due to expansion or the clearing out of the local material. So what's happening to the PRS? So here we have been also monitoring the PRS with Meerkat over the years. So here I just show the light curve of the PRS. So we have Meerkat observations in 2019, 2022, and 2024, and also continuing through 2025. So the inset shows this Meerkat observation, high cadence Meerkat observation, happened in 2024. So we find that this flux density of this PRS is exhibiting variability in the order of like within weeks to month timescales. And such a flux density variation is also well described by refractive scintillation, which can predict a modulation amplitude of 25%. And we find no evidence for long-term variation in the flux density with this source. And some detailed analysis on this scintillation is also yet to be undertaken. Also, so yeah, as a summary, the MITRA discovered a hyperactive repeater. So we have been long-term monitoring this source, and our observation revealed an exceptionally high burst rate. So most of the bursts are linearly polarized and exhibiting like modest variation in the PA angle. So long-term monitoring is crucial to understand whether the source will become active again or will remain as an isolated outburst event. And no PRS has been detected across a frequency range from 0.5 to 12 gigahertz. And we found an evidence of RM evolution with no significant evolution in the DM. And also long-term monitoring of R1 indicates that the DM is declining at a rate of 0.01 parsec per cubic centimeter. And the flux density variations is agreeing with the predictions from refractive scintillation. Thank you.
Thanks, Kavya. Do we have any questions? You? Okay.
Hi. Yeah, thanks for the great talk. I'm wondering about FRB 121102. If you combine the change in dispersion measure with the change in rotation measure, what sort of magnetic field do you get? I'm wondering because it seems like it would be a cleaner measurement than just the RM alone, which requires knowing the host DM, which we don't.
Yeah, I think I haven't done such an estimate because we don't have RM measurements alone from Meerkat, but we have RM estimates from like other telescopes, but we have values till 2023. But all these measurements of Meerkat is also from 2019 and 2022 and 2023. So we don't have simultaneous like RM measurements, but it's it's a good analysis to check whether there is any like the estimate of the magnetic fields with the estimate. Yeah.
We have another question for there.
This is Brian Gainsler from UC Santa Cruz. Thank you for that talk. What can you say from the latest data about the possible periodicity in R1's activity period that had been suggested previously?
So could you repeat the question again?
So there had been a claim of a possible periodicity, 160 days. So does your newer data through to 2025 support that or lower the significance or not sure?
So I can just show here. So we have detected burst only in 2019, 2022, and 2023. These are well within the activity phase described by the 160 days periodicity. We don't have further burst detection in 2024 or 2025. But recently, I also saw in an ATEL that in like 2 months back, the source has become active again, and this is consistent with the predicted periodicity cycle. But we don't have any detections from Meerkat.
But you were observing during the predicted activity periods and didn't see anything in 24.
We had a single observation in the last May in the predicted periodicity, like within the active phase, but we did not detect any bursts in 2025.
Thank you.
Okay, we have time for a short question. So one over there.
Where am I throwing it?
Nice.
Hi, Marilyn here. I was wondering regarding the follow-up of 121102. So do you observe it like randomly when you have some time to observe it, or when you think it's detected or there is some indication that was active?
So the observations happened in 2019 and 2022 were like 2022 and 2023 were DDT observations. So we had only like few observations within the activity cycle. But the observations happened on 2024. was like we had the Meerkat proposal and we got time. So we arranged the observations in a such a way that like it was in a logarithmic fashion within the activity phase, also in the inactive phase. So that's why we had like 3 observations within a week. Then the separation between the observations increases like in a logarithmic scale. Yeah.
Thank you.
Okay, if you have any more questions, please ask them during the coffee break or on Slack. Let's thank our speaker again.
Should I just skip this?
And now we have 2 flash talks. Just a note that we have switched the order of the speakers that were scheduled.
Those Google Slides, yeah.
Can you hear me?
All yours.
Can you hear me in the back? Great.
Okay, so our next speaker is Thomas Abbott. So please go ahead.
Thank you. Yeah, so I'm Thomas. I'm a master's student here at McGill, and I work with Professor Vicky Caspi and Dr. Aaron Perlman. And today I'm going to be presenting some results from a long-term monitoring campaign using the Chime Pulsar instrument on FRB 2022-09-12A. So because it hasn't been introduced yet, I'll just talk briefly about the Chime Pulsar instrument, which uses the same front end as Chime FRB, but it differs in the back end. So Chime FRB, as we've seen, forms these static beams in a strip along the sky and scans the northern sky every day. Chime Pulsar, on the other hand, has digitally formed tracking beams, so we can point at a source and follow it through its transit. So it's a little bit better optimized for targeted follow-up. And in particular, we use it a lot for follow-up of repeating FRBs. So in this talk, I'll be describing or discussing 2022-09-12A. A lot of you have already written papers on this source or are familiar with this source, but it was discovered in 2022 by Chime FRB and quickly localized by the DSA. And then later that was improved to Milliarcsecond localization by the EVN. And most notably, it had an enormous detection rate, over 400 bursts, or about 400 bursts an hour from FAST. And there have been a lot of other scientifically interesting results from this source, including microshots, a drifting central frequency over time, and as I'll discuss today, some DM variation. So basically in this project, we study the source for about 2 years. We have 20-minute observations every day, amounting to over 200 hours of observation with Chime Pulsar. And we detect about 800 bursts from the source. And just by calculating the total energy emitted, this is a very rough estimate, sort of back of the envelope calculation, but I think it's an interesting result nonetheless. If we calculate the total energy emitted by the source and approximate scaling up for times we're not observing and also for the radio to X-ray fluence ratio, we get an energy emitted over this 2-year time span of something like 10 to the 40 ergs, which is already getting sort of within an order of magnitude or so of the amount of energy stored in a magnetar's magnetic field. So I think this is further motivation for following up these hyperactive repeaters as they can test some magnetar models. Okay, and the other result is over the 2-year time span, we saw a pretty steady linear increase in the DM of about 1.3 parsecs per centimeter cubed per year. This is using the brightest, narrowest bursts. You can see that increase. And interestingly, there's no corresponding change in the RM. It remains consistent with 0 throughout the observations. So yeah, I'll just stop there. I think I'm out of time. Thank you.
So much. Have any questions from the public? No? Maybe like, are you also following up other repeaters that show similar properties, or is this the only one so far?
Yeah, we're following up a few repeaters. Mostly our campaigns are dedicated to nearby repeaters, and we want to trigger high energy follow-up. But with a lot of those sources, we just don't detect any bursts.
Okay.
So it's a bit of a mix with nearby and kind of high-risk campaigns and also hyperactive.
Okay, yeah, thank you so much. Any other questions or online? Okay, if not, let's thank our speaker again. And lastly, we have a pre-recorded talk by Param and Joshi. And
Okay.
I believe Param is online to answer questions as well. It was.
Yeah, that was a PDF. All right. Oh, sorry, and just anticipating an audio problem. Once I start it,
Hello
if people
everyone,
on Zoom
I'm
can
Param Joshi.
that we hear it. Oh, sorry, I need to restart this. I lost my Chrome window. Sorry. Because I think I need to reshare the screen with a audio shared. Could be. Oh, great. So we were golden.
Hello everyone, I'm Param Joshi, final year master's student studying at National Institute of Technology, Rourkela, India, and I'm also currently an astronomy student. Today I'm going to talk about this particular FRB and our observations with the LN telescope array. So let's first begin with a bit of an introduction on the telescope. It is an array of 42 antenna dishes, which is spread across the Hat Creek Radio Observatory in California. And each antenna is 6.1 meter in diameter, and it covers a bandwidth of 1 gigahertz up to 11 gigahertz, with 2.68 gigahertz of instantaneous bandwidth. And currently 28 out of the total 42 antennas are being used at 672 megahertz wide and independent bands simultaneously. So let's start with some of the observation statistics. We observed this source for a total of more than 1,000 hours and at frequency ranges of 900 megahertz all the way up to 7.6 gigahertz. And we have detected a total of 97 bursts using the SpunDuck plus ML pipeline. And the bursts covered the frequency extent from 900 megahertz to 5 gigahertz. And the fluence ranges was 15 to 300 Jansky milliseconds. And the bursts show some usual subburst structures and downward drifting patterns. So on the right, we have the plots for the on-sky time of the source as per the frequency that we observed. And the below plot is just a random subburst showing structure of the FRB. So these are our results with the LN telescope array. And we detected around 20 bursts, which are wideband in nature, with a bandwidth of 800 megahertz or more, and burst energy of more than 10 to the power 40 ergs for these particular wideband bursts. And the burst rate was observed higher in S band than L band, but we are still investigating the impact of RFI in L band and also some issues with the pipeline that it could not detect the very low SNR bursts maybe. And yeah, it is also possible that due to either higher burst clustering at S band than L band, or maybe it was an active period of FRB at the time we were observing the S band. So on the right, we have the plots for the burst rate and as per the frequency. And the below plot is for the burst clustering. We can see that the clustering is higher in like S band around 2500 or 3000 megahertz. And also we have a higher burst rate at around 3000 megahertz. So that may be possible because of that. So these are some of the detection plots. It is a beautiful FRB showing various substructures of the burst, and it's also having very wide band emissions and highly energetic bursts. So yeah, this is going to be my future work to study all the spectrotemporal analysis of the burst with some properties like width, drift rate, bandwidth, and analyzing all its variations with frequency, and also some burst energetics and rate and clustering. And yeah, please feel free to reach out to me for any questions or comments. And I'm open for any questions if we have time, and I'll be online as well. Thank you.
For Param. If not, since we're a bit short on time, we'll go to the coffee break now. We have until 3:30, so 20 minutes. So see you again then.